In this lesson, I want us to look at what we can actually do about tsunamis. At the start of the last lesson, you might remember that I started out by playing you what the tsunami warning siren sounds like. This is the location where that warning siren is triggered. It's the Pacific Tsunami Warning Center based in Hawaii, and they monitor seismic activity from right around the Pacific region and use that to generate predictions about whether a tsunami has been generated and when it's likely to hit the different areas around the Pacific. We'll look a little bit about how they do that later on. We've already established that tsunamis have the potential to be devastating. So being able to predict a tsunami is crucial because it is possible to do something about it, principally to get out of its way. But let's have a look at how this happens. The first and perhaps key part of this to preserving life is an early warning system. Tsunamis travel very quickly, but they travel, as we'll see, enormous distances. That takes time. So it is possible, in a lot of occasions, to get a warning that a tsunami is on its way. To do that, we need to be aware of actually what's happening in other parts of the world. So the Tsunami Warning Center will, first of all, be monitoring seismic activity. When a large earthquake is detected underneath the ocean, that will start the process of looking for a tsunami. But earthquakes under the ocean will only generate a tsunami if we get a displacement of the seabed. If the earthquake only breaks rock below the surface, it won't have an effect on tsunamis. It won't generate a tsunami. If we do have an earthquake that generates a tsunami, this then can be detected in a number of different ways. Firstly, by the seismometers, but also through a series of tsunami detection buoys. This is shown on this diagram that you have a copy of on page 21 of your booklet. These tsunami buoys in the ocean detect the changing pressure in the water. They detect the wave actually in the ocean. That can then send a satellite warning to the Tsunami Warning Center, who can then start triggering the warnings in the places that are likely to be affected when they're likely to be affected. This can be a very effective method, although there is one fundamental weakness. We'll come back to that later. But the Pacific Ocean, which has 80% of the world's tsunamis, actually most of the time can deal with certainly the threat to life that a tsunami might cause. In addition to the warning systems, there are also some engineering features we can place around the coast to protect from tsunamis. That could include barriers of trees, or even designing buildings to be able to deal with the effects. Let's have a look at what these might be. At the bottom of page 21, you have this diagram. There are 4 different strategies that are shown on this diagram, each of which can help to reduce the effect of a tsunami. What I'd like you to do is I'd like you to explain how each one of these could reduce the effects of a tsunami. So press pause now and have a go at that question. Okay, let's see what you've come up with. So this is, I suppose, an idealised diagram of what a coast could be. Let's start from the sea going inland in the same way that a tsunami would. This development-free zone of parks and forests act to slow down the water. The tsunami having to flow through the trees, around the trees, particularly trees like mangroves, for example, which have evolved to cope with these conditions, will slow the wave down. And if there's no property there, there's no property to be damaged. If we then look at design C, if buildings are built at right angles to the coast, and actually built up on like stilts or concrete piles, that keeps the property above the height of the water. So if we look at strategy C, this is to put buildings side on to the coastline, and also to put them on stilts, on concrete piles. Now, the idea behind this is it keeps the property above the height of the water, so that the tsunami can swirl around underneath the building, but the building itself won't be destroyed. Now, both of those strategies are great in theory, but you've got to remember that coastal property is extremely valuable. For example, I've seen in Sri Lanka, since the Boxing Day tsunami in 2004, that had a big effect on southern Sri Lanka. New hotels are being built right on the edge of the beach. Even though they're going to be vulnerable to another tsunami, that's where people want to stay. That's where, as a result, we'll have some Sri Lankans putting developments there, even within sight of areas that have been devastated during the Boxing Day tsunami. Similarly, the houses built on stilts, well, that's going to be more expensive. It's going to be less convenient, I suppose, for people living there. Are people going to do that? Strategy B is to build an embankment to act as a barrier to water moving inland. Great idea, but we've seen in the Sendai earthquake, embankments that had been built there to keep tsunamis back were overtopped. The tsunami was just too high. It was higher than had been predicted, and the embankment as a result failed. The final strategy, a coastal road that's higher, raised up from the surrounding land. That does provide another barrier. Also, it allows for easier evacuation, easier access perhaps to the disaster zone. So engineering is part of this, but it's not the only solution. The maps that you have in black and white in your booklets, I'll also attach colour versions of this to the lesson guidance notes, show the travel times for the tsunami waves for these two big tsunamis we've been looking at. The one on the left is the Boxing Day earthquake in the Indian Ocean. The one on the right is the Sendai earthquake in the Pacific Ocean. What I'd like you to do is to use these maps to answer the questions on page 22. Now, it'll help if you've got an atlas or possibly Google Earth or just searching in Google to find, and Google Maps perhaps, to find the locations that are mentioned. Okay? Have a go at that now. Press pause and we'll see what you can come up with. Okay, let's see what we found. Question A, I asked for which direction the Indian Ocean tsunami travelled, and it was generally to the southwest. The Japanese tsunami generally travelled to the southeast. If you look at the time it took to get to these various places, to get to Sri Lanka, the Indian Ocean tsunami took 2 hours. To get to Madagascar, it took 8 hours. To Australia, 5 hours. And Antarctica, 11 hours. You can see that these travel times can be very long over the huge distances across these oceans. For the Japanese tsunami, to get to Japan, it was less than an hour. That's really significant. For Hawaii, though, it was between 7 and 8 hours. For California, 10 hours. For New Zealand, 12 hours. Chile, 21 hours, nearly a day later. And Antarctica, 17 hours. So you can see these travel times are enormous. But the Indian Ocean tsunami in 2004 caused a great deal more deaths than the Japanese tsunami, even though they're both fairly horrific events. The reason for the difference, though, was that in the Pacific, they're prepared for tsunamis. There are warning systems in place. There are quite a few wealthy countries around the Pacific Ocean, the US, Australia, New Zealand, Japan, that will spend the money to put the warning systems in place and to keep them running. The countries around the Indian Ocean, which is much less likely to have tsunamis than the Pacific Ocean, because there aren't as many convergent plate margins, they don't have that in place. And as a result, a lot more people died. Okay. Just something to think about as we finish. We may think these issues are a long way away. This image you can see is a woodcut representing what happened on the 30th of January 1607 in the Bristol Channel. There was a massive flood event that swamped parts of South Wales, the low-lying parts of Somerset, that geologists think was actually caused by a tsunami. Should we be worried about this here? Should we have tsunami defences in place? What do you think? Okay. As we watch the sunset over Flatholm Island, if we think about this, it is possible to give a warning that this event is going to happen. The travel times across these major oceans are big enough that warnings can be given, people can get to places of safety. You know, if you can go up a hill, 20 metres up a hill, the tsunami isn't going to get you there. However, if you live close to the epicenter of that earthquake, if that tsunami arrives in perhaps a matter of minutes rather than many hours, your chances of getting a good warning and then being able to do about it are much, much reduced. Most of the death tolls in tsunamis, with the exception of the 2004 one, happen less than an hour's travel time for the tsunami from the earthquake epicenter. So although it's possible to do something about these hazards, we can't take away the risk altogether. Okay. Next time we're going to move on to look at another type of geological hazard. I'll see you then.